you. Good afternoon. Hiro, thank you so much for your kind introduction. Hiro and his wife Betty have been the mentor of me and of my family for the last several years. And Hiro has been my golf coach. Approximately a year ago, I got a phone call from Stockholm. It was the chairman of the Nobel selection committee. And he told me, we have decided to award you this year. And then he said, would you accept? So I said, yes, why not? Then he said, well, Shinya, I'm glad to hear that. But this is going to be confidential for the next 2 hours. But as soon as I finished that phone call, I broke the embargo and I called to Hiro. So I hope this works. Oh, too much. So today I would like to talk about VW. I will not talk about German automobile. I will talk about my own motto. So I started my career as a surgeon, as a doctor, not as a scientist. It was my father who talked me into medicine. This is my father who passed away 26 years ago. I respected him a lot. I liked him a lot. I liked his hair. I am actually envious. My father was a businessman. He had a small factory in a small city called Higashi Osaka in Osaka area. I am his only son. When I was born, my father must have been happy to have a successor of his business. However, when I became a junior high school student, he started saying this way, Shinya, you should not take over my business. You should become a doctor to help patients. I don't know why he said that. Maybe my father thought his son was not smart enough or brave enough to be a businessman. Or maybe he thought his son was too honest to be a businessman. I don't know. So, just joking, I'm sorry. So I listened to his opinion and I became a doctor. I became a surgeon. When I was doing my residency, he passed away, when I still needed him a lot. He must have been in pain before he died. But he did seem happy by receiving some medical procedures from his own son. He must have been proud that his son became a doctor. When I was doing my residency, I saw many patients whom we couldn't help at all, like patients suffering from spinal cord injuries, patients suffering from Lou Gehrig disease. I started thinking that it would be basic medical research that could help these patients. At the same time, during my residency, I found myself not talented at all in surgery. Actually, I was terrible. So I thought I wouldn't be able to help any patients by doing surgery. It was dangerous, actually. So I decided to change my career. I escaped from hospital and I entered a graduate school. And I got my PhD in pharmacology in 1993. And after that, I decided to continue my training as a scientist. I went to San Francisco. I became a postdoc at Gladstone Institute. You know, I sometimes feel, I'm afraid that my father is very angry, saying that, Shinya, stop shaking test tubes, come back to clinics. But I decided to continue my research. And this picture was taken when I was in San Francisco with my boss, Tom Indenarity. The purpose of this slide is to show you that I used to have more hairs. So, here comes VW. This is the then president of Gladstone Institute, Dr. Robert Mealy. He had, and he still has, VW. But one day, he taught us, young scientists at Gladstone, how to succeed as a scientist. And he said, it's simple. We have to follow VW. Well, I had Toyota, so I thought, well. But he said, in this case, VW does not mean Volkswagen. This case, VW means vision and work hard. Well, it's very simple message, but it was a very strong message to me. You know, I was, and I am, still working very hard. I'm confident. However, when I was asked what my vision was, I could not answer immediately. Is it to publish papers? Is it to get funding from NIH? Is it to receive awards? No. I recall my initial motivation to be a scientist. My vision is to help patients, is to develop new cures for patients suffering from intractable diseases and injuries. So from this moment, I always keep this simple message, VW, in my mind. Also at Gladstone, I met very important cells, embryonic stem cells, ES cells. ES cells were first generated by scientists in the States and in UK from mouse embryos in 1981. Mouse ES cells have two important properties. We can expand mouse ES cells as much as we want. Then we can make many types of cells from mouse ES cells in a large amount, like brain cells, heart cells, blood cells, and so on. So mouse ES cells have been very useful in biology. Because of this importance, Dr. Martin Evans, who first generated mouse ES cells, received Nobel Prize in 2007. After spending 3 years at Gladstone, in 1997, I and my family went back to Japan. I continued my research on mouse embryonic stem cells. But after a year or two, I became sick. The name of my disease is PAD. PAD stands for post-American depression. So when I was at Gladstone, I was surrounded by many top-class scientists. I was surrounded by many supporting staffs. The scientific funding was very good. But after going back to Japan, I lost all those stimulating environment. So that's why I became depressed. I was not sure whether I can really realize my vision by doing science. I was often told by my colleague, Shinya, you should stop working on mouse cells. You should do something more related to human patients. Do you want to be a mouse doctor? So I was about to quit from science and go back to clinics. But very luckily, 2 events happened that rescued me from PAD. The first event was happened in 1998. Dr. Jamie Thompson in Wisconsin, he generated human embryonic stem cells from human embryos for the first time. Human ES cells have the same 2 properties as mouse ES cells, in that we can expand human ES cells as much as we want. Then we can make various types of human cells in large quantities, such as dopaminergic neurons, neural stem cells, heart cells, and so on. Then we could transplant these human cells into patients suffering from various diseases and injuries, such as Parkinson's disease, spinal cord injuries, heart failure, and so on. So it turned out that ESL research, my research on mouse ES cells, could contribute to human health. So I was very excited. However, human ES cells face a severe ethical obstacle. We have to use human embryos. We have to destroy human embryos to generate human ES cells. So many people are still against the usage of human ES cells, including these 2 important leaders of the world at that time. I don't think you can, read this sentence here. I cannot read by myself, but I think it says President Bush and the Pope talking about something bad about human ES cells. They were totally against the destruction of human embryos. So I knew the potential of human ES cells were enormous, but at the same time, the hurdle was very high. The second event that rescued me from PAD was my promotion to this new institute, NARA Institute of Science and Technology. As you can see here, this institute has a very beautiful campus. They have many good scientists. They have many supporting staffs. They have good fundings. And most importantly, they have many talented and hardworking graduate students. I got my own laboratory for the first time in my life. So because of these 2 events, I was able to overcome my PAD, and I was able to continue my research. In this new and good scientific environment, I decided to pursue this goal. I wanted to overcome the ethical hurdle of human ES cells. We wanted to make ES-like stem cells directly from adult, like skin cells or blood cells. If we could do this, we can avoid the usage of human embryos, so we can overcome the ethical issue of human ES cells. Of course, I knew this was very difficult. I thought it would take 10 years, 20 years, or even longer. But I did not tell that difficulty to my students. I just told them how wonderful it would be if we could do this. And, I got 3 very talented graduate students and some staff members. They worked very hard, and to our surprise, it did not take 20 years. In 2006, after 6 years after we initiated this project, we became able to convert mouse skin cells into stem cells that are very similar to mouse ear cells. The procedure was surprisingly similar. All we have to do is just add 4 factors, more precisely 4 genes into mouse skin cells. Adding genes is very simple. Even high school students can do that procedure. We designated these new stem cells IPS cells, induced pluripotent stem cells. And the following year, in 2007, we and 2 or 3 other groups in the States were able to recapitulate the same iPS cell generation in human. I want to tell you that it was not myself who actually generated iPS cells. It was many of young students and supporting staffs in my laboratory. Especially these 3 scientists, young scientists, were essential. Yoshimi and Kazu were 2 of my very first graduate students. Tomoko was my first supporting staff. So without these 3 young scientists, we could have never generated iPS cells, at least in my own laboratory. Well, I have 2 daughters who are a bit younger than these 3 persons, but these 3 persons are almost as important as my daughters. Oh, I forgot to tell you, I have a wife. She is more important. So let me show you how we make iPS. Don't start. Just wait. So in the beginning, we generated iPS cells from skin cells. But in order to do that, we have to ask skin biopsy from donors. It's not a difficult procedure. Even I can do that. But still, we do need anesthesia. We do need a stitch. So it's not the best way. Another group in San Diego, they have developed a way to generate iPS cells from a single hair. It's much easier. However, single hair means a lot, at least to me. So, could you stop the video? Could you? Yeah, I'm sorry. So instead of using skin cells or instead of using single hair, we have developed a way to generate iPS cells from blood cells. So now, could you start the video? I'm sorry, I think you saw it already. So it's very simple. All we need is a simple blood sampling. And then all we have to do is add those factors onto your blood. Then the 4 factors, 4 genes described here, will go into blood cells and initiate the process of iPS cell generation, also known as reprogramming. So they start proliferating, and they gradually become iPS cells. And so this is a microscope image of iPS cell generation. I hope you can see cells proliferating very rapidly and form iPS cell colonies. So if we add some drugs to iPS cells, we can make many types of cells, like beating heart cells from iPS cells. So this is a microscope image of beating heart cells from iPS cells. When I first saw this 7 years ago, my own heart synchronized. So we can use these heart cells or brain cells, liver cells, blood cells derived from iPS cells in 2 types of medical and pharmaceutical applications. We could transplant heart cells derived from iPS cells back into patients suffering from heart failure. So instead of organ transplantation, which is still very difficult in Japan, we may be able to save patients suffering from very severe heart failure. By transplanting neural cells into patients suffering from spinal cord injuries, we may be able to treat those patients. Alternatively, we could use these brain cells, heart cells in laboratories. We can make disease models, and we can perform drug screening. So there are 2 types of medical and pharmaceutical applications. So we now have more focused vision. We want to make this happen. We want to bring iPS cell technology to patients. It's not my vision. It's the vision of many scientists all over the world. There are strong scientific activities both in Japan and in the States. Actually, the States has even a stronger activities for iPS cell research. So in order to achieve this goal, I have been working in 2 places, in Kyoto and in San Francisco. In Kyoto, in Center for iPS Cell Research and Application, we have more than 200 people working on iPS cells. In San Francisco, since 2007, I rejoined Gladstone Institutes. They now have this beautiful building in the newly developed Mission Bay campus near the baseball stadium in San Francisco. At Gladstone Institute, I have a smaller but excellent group. I brought 2 Japanese postdocs from Japan to San Francisco. So again, there are very strong activities in 2 nations. It is essential to connect the activities in the 2 nations. Strong collaborations are essential to promote this technology to clinics. Well, I did receive the prize last year, but the truth is, we have not been able to help any patients by this technology. We still have to work very hard. So I really hope we can bring, with the help of many scientists in Japan, in the States, and in many countries, we can bring this technology to patients. I hope we can do that before I meet my father again in the near future. Thank you very much.